Get ready for a dramatic increase in technological development. DeepMind, a Google subsidiary, claims to have discovered 800 years' worth of knowledge after discovering 2.2 million new crystals. Google DeepMind stated in a blog post that 380,000 of these materials are stable and could power future technologies ranging from next-generation computer chips and batteries to solar panels. The discovery of new materials with unusual properties can set off technological snowballs that eventually push society in new directions, but it's been a painfully slow process involving a lot of trial-and-error experimentation up to this point. GNoME graph networks for materials exploration, a cutting-edge neural network tool, made the discovery. Hello and thanks for tuning in. Before we go any further, please take a moment to support us by liking this video. Subscribe and activate the bell notification feature so you'd always know when we put out new videos. And remember, sharing is caring. Okay, let's get back to it. Inorganic crystals are used in a variety of modern technologies, including computer chips, batteries, and solar panels. Crystals must be stable in order to enable new technologies, otherwise they will decompose, and each new, stable crystal can be the result of months of painstaking experimentation. Inorganic crystal materials, for example, may show enormous promise when first synthesized, but all of this promise may be for naught if the crystals do not remain stable. It's no good discovering that a new crystal could improve the performance of batteries or electronics if it will fall apart and degrade. That's where DeepMind's graph networks for materials exploration, GNoME, deep learning tool has just made a hugely disruptive announcement. DeepMind shared the discovery of 2.2 million new crystals, equivalent to nearly 800 years of knowledge, in a paper published in Nature. Graph networks for materials exploration, GNoME, is a new deep learning tool that predicts the stability of new materials, dramatically increasing the speed and efficiency of discovery. GNoME has increased the number of technologically viable materials known to humanity. 300,000 of its 2.2 million predictions are the most stable, making them promising candidates for experimental synthesis. Materials with the potential to develop future transformative technologies such as superconductors, powering supercomputers, and next-generation batteries to improve the efficiency of electric vehicles are among these candidates. GNoME demonstrates the potential of using artificial intelligence to discover and develop new materials at scale. In parallel work, 736 of these new structures were independently created by external researchers in labs around the world. A team of researchers from the Lawrence Berkeley National Laboratory published a second paper in Nature in collaboration with Google DeepMind, demonstrating how DeepMind's AI predictions can be used for autonomous material synthesis. Approximately 20,000 of the experimentally identified crystals in the ICSD database are computationally stable. Computational approaches based on the Materials Project, Open Quantum Materials Database, and OBBM database increase the number of stable crystals to 48,000. GNoME brings the total number of stable materials known to mankind to 421,000. Previously, scientists sought novel crystal structures by modifying known crystals or experimenting with new elemental combinations, an expensive trial-and-error process that could take months to produce even limited results. Computational approaches led by the Materials Project and other groups have helped discover 28,000 new materials over the last decade. However, new AI-guided approaches have hit a fundamental limit in their ability to accurately predict materials that could be experimentally viable up until now. GNoME's discovery of 2.2 million materials is equivalent to approximately 800 years of knowledge and demonstrates an unprecedented scale and level of prediction accuracy. 52,000 new layered compounds, for example, that are similar to graphene and have the potential to revolutionize electronics through the development of superconductors. Approximately 1,000 such materials had previously been identified. In addition, we discovered 528 potential lithium-ion conductors, which is 25 times more than in a previous study and could be used to improve the performance of rechargeable batteries. DeepMind will also reveal the predicted structures for 380,000 materials that have the best chance of being created in the lab and used in practical applications. To be considered stable, a material must not decompose into similar compositions with lower energy. Carbon in a graphene-like structure, for example, is more stable than carbon in diamonds. These materials are mathematically located on the convex hull. This project discovered 2.2 million new crystals that are stable according to current scientific standards and are located beneath the convex hull of previous discoveries. 380,000 of these are considered the most stable and lie on the final convex hull, the new standard for material stability. GNoME discovers low-energy, stable materials using two pipelines. The structural pipeline generates candidates with structures that are similar to known crystals, whereas the compositional pipeline uses a more randomized approach based on chemical formulas. Both pipelines' outputs are evaluated using established density functional theory calculations, and the results are added to the GNoME database to inform the next round of active learning. GNoME is a cutting-edge graph neural network (GNN) model. GNN input data takes the form of a graph that can be compared to atom connections, making GNNs particularly well-suited to discovering new crystalline materials. GNoME was initially trained using data on crystal structures and their stability obtained from the Materials Project. GNoME was used to generate novel candidate crystals as well as predict their stability. We repeatedly checked our model's performance during progressive training cycles using established computational techniques known as density functional theory (DFT), which is used in physics, chemistry, and materials science to understand atom structures, which is important for assessing crystal stability. The active learning training process was used, which significantly improved GNoME's performance. GNoME would predict the structures of novel, stable crystals, which would then be tested using DFT. The high-quality training data that resulted was then fed back into our model training. Based on MapBench discovery and external benchmarks set by previous state-of-the-art models, DeepMind's research increased the discovery rate of materials stability prediction from around 50% to 80%. We also increased the efficiency of our model by increasing the discovery rate from less than 10% to more than 80%. Such efficiency gains could have a significant impact on how much compute is required per discovery. The goal of the GNoME project is to reduce the cost of discovering new materials. External researchers created 736 of GNoME's new materials in the lab independently, demonstrating that the model's predictions of stable crystals accurately reflect reality. The ability to manufacture these crystals will be critical for rapidly developing new technologies based on them. In a paper led by Berkeley Lab scientists, researchers demonstrated how a robotic lab could rapidly create new materials using automated synthesis techniques. The autonomous lab created new recipes for crystal structures and successfully synthesized more than 41 new materials using materials from the Materials Project and insights on stability from GNoME, opening up new possibilities for AI-driven materials synthesis. This pair of projects could pave the way for untold technological advancements, and they are a stark example of the radical upheaval that artificial intelligence systems are already causing in nearly every aspect of life. Buckle up, people. And that concludes today's video. Do let us know what you think about today's discussion in the comments section below, and you can support this channel by liking this video. Subscribe and activate the bell notification feature so you always know when we put out new content. And remember, sharing is caring. Take care and see you in the next video.